So these are chapter 32 homework problems. I'm just going to go through a few of these things. We talked about some in class. We whiteboarded some in class. 5 was a little bit annoying because it was really the point source for the Biot-Savart law. What I said is this part really is looking at the cross product. So it's looking at what component of these factors do act in a way that's perpendicular to the direction of motion of this charge, therefore which of those actually cause a magnetic field. So it's into the board or into the page, comes out to this strength, and again, I think you can look at the formulas for that to help figure it out. But basically we're looking at this point here caused by a charge moving at this point here. Number 14 is looking at the field strength at different points A, B, and C. I think we talked about this in more detail in one of the classes. We may or may not have done it in the other class. So we've got this, which is 2 centimeters from the top wire, 6 centimeters from the bottom wire. So the key thing is figuring out the magnetic field strength at those 2 centimeter and 6 centimeter distances, which I had initially screwed up, so that's why that's whited out. Really, I probably would only need to do this calculation, and since only the distance changes, I could divide this amount by 3, which would give me this amount. So essentially, if I'm looking at the net field, not the net force, but the net field, I need to figure out, well, what effect does this wire have at this point? What effect does this wire have at this point? And then what effect do each of those wires have at point B and point C? So there's a lot of symmetry here. Obviously, the wire that's closer will have the bigger effect. In the middle, the wires would have the same effect since the point B is the same distance from them and they have the same current. So the math is down here. I talk a little bit more about that in detail down here. Hopefully you can read my writing. I get the net field here, here, and here. So the reason the net field is not 0 at this point is because both the bottom wire and the top wire at point B in between them have fields going in the same direction. So if we were to talk about forces, these two wires would be repelling each other when they have currents going in opposite direction. I screwed up here. I did 21 instead. If you want to look at that, that's fine. Or 22 instead. 21 is actually at the end. 33, we're looking at the fact that a magnetic force upward would equal gravitational force downward. So it's basically a magnetic field to levitate that 2-gram wire. F grav equals F magnetic, mg BIL. So I probably should have put that up there. So that ends up being 0.131 Tesla. I use the flat hand rule to determine that for an upward magnetic force and the current going to the left, I need the field coming out of the page. 34, I think we talked about. So we get a net force of 0.025 newtons to the right. Given the size of the loop, we could use Ohm's law to figure out the current. 10 centimeter section, top and bottom panels would have a force on them, but that would be in the opposite direction, so no net force caused by that. Take a look at 36. 36, I did an example in class. Here we're looking at forces on the wires. Again, I think I showed a lot more work than I probably needed to. And I essentially was figuring out the forces between the top and middle wire, top and bottom wire, bottom and middle wire. And there's a symmetry here. So the net force on the top wire, net force on middle wire, net force on bottom wire. This is a version of the formula we would use. Again, it's a derivation of this combined with that. So this is magnetic force on a wire. This is a version of the Biot-Savart law for a long wire. And a long wire means basically just anything other than a point source is what we think about that as. So again, the reason there's no force on the middle wires, the top and middle have have a repulsive force. The bottom and middle have a repulsive force, so again, no net force. 50. This was the one problem we had with a solenoid. This is the formula that I think is on your formula sheet, mu o lowercase n sub n times I. Basically, lowercase n is turns per meter, so I changed that into n turns over L meters in length. Figured it out that way. 60, I think we did talk about in class also. Key thing is here, you need to know the charge on an electron. 1.6 times 10 to the negative 19th coulombs. It's negatively charged, therefore it'd be attracted to the top. Therefore, the magnetic force has got to be pointing toward the bottom. I show that in my free body diagram here. Show those as being equal. I take a little bit more time than I think people did in class to show how I come up with the electric force. And then I simply put that into the QVB formula. I get that 0.02 Tesla is directed into the page because with the left-hand rule, if I have a magnetic force down, the magnetic field is pointing into the page. I think I did 68 as an example in class. I like this because it basically is looking at the force on this wire caused by springs. So I've got the free body diagram over here. Two springs, each with a certain strength, so the net force caused by the springs is 0.2 newtons to the right, so therefore magnetic force is 0.2 newtons to the left. This is 21. Again, I don't think this is going to be super critical. If we have a clockwise arrows drawn here, that basically means into the page is positive, out of the page is negative. So it said that the value of this line integral is this value. Since that seems to be positive, I should have more current going into the page than out of the page. So I told me my net current into the page was 3 amps. Based on the other information that's given, that means that I3 would have to be 7 amps into the page. Hopefully that makes sense. I also obviously have a PDF, so hopefully you'll be able to understand those if you did not while you were doing them.